but we have the workshop the next week. So, yeah, wait for the surprise. And we have the last class by Esteban Sepúlveda. Gracias, muchas gracias, Esteban, por estar aquí.
Nada.
Thank you, guys.
Can you hear me? No. No? Yes. I can't, but...
Who said no? Okay. Yeah. And, well, I guess that you are very tired after this awesome week, right? So this class will last 10 minutes? No, well, while we're waiting for the slide, yes, thank you very much. I would like to review some concepts that I told you the last, I think it was Wednesday, I think, about quantum measurements. Okay, we have at least two kinds of quantum measurements: the projective and the non-dichotomic or generalized quantum measurement or non-projective measurement. And we talked about how we can certify if a POVM is actually a POVM. Remember that we can build a model in which a POVM, the statistics from a POVM can be fitted using projective measurements. And if, okay, I'm showing you the wrong slides. Thank you for sending me that. I don't know what is happening here. Yes, I think that. Okay, let's go forward. This is the idea. Okay, let me remind you this idea. We have an untrusted device, which in principle implements a three-outcome measurement over a qubit. Okay, but the working mechanism of this device is select randomly between three dichotomic measurements, and then depending on the results of this projective measurement, we can have the three outcomes. Okay? And the next question that we can do is how we can certify if an untrusted device is actually implementing a POVM. And the first way is through implementing a device-independent scenario. And the device-independent scenario is, if you remember, probably Steve talked about the device-independent Gauss, yeah, I think too. The device-independent scenario is related to the violation of Abelian inequality. To violate Abelian inequality, you need entanglement. But it's possible, okay? Well, Bertesi and Bennett have proposed a Abelian inequality in which the maximal value that we can reach using quantum mechanics is resorted to the use of POVM. We, in the past, performed an experiment in which we use this inequality. No, I can't use my super laser beam here. My pen. This is the inequality. Okay? This inequality has two parts. This is something like the CH-SH inequality. We will take about later about this inequality, and it has this term. If you are not familiar with this notation of the probabilities, I can explain briefly. The notation is the following, and the notation says that if in this case, if Alice performed the X measurement and the outcome of this measurement is A, and Bob performed the Y measurement and he obtains the result B, we can construct this probability, right? So this inequality requires two measurements in the Alice side, three measurements on the Alice side, three measurements in the side of Bob, but also for the terms related to the POVM, Alice needs to implement a fourth measurement, which is a POVM. Okay? So we can resort to all the strategies using just non-dichotomic, resorted to the dichotomical, resorted to just for projective measurements in order to obtain what is the maximal value allowed by quantum mechanics of this inequality. Okay? And then we can calculate what is the maximal value if we use the POVM. And we can find that, there is a gap between the projective bound and the POVM bound, which correspond to the quantum maximal value of this inequality. Right? So, in order to certify if my device, which I'm using testing this inequality, just I need to perform the experiment, compute the probabilities, and then I have to look if the value of my inequality is in the region of the non-projective measurement or is in the projective measurement. Okay? Do you have questions?
Are you fixing the quantum state or the dimension?
Okay, yeah. For this inequality, you need to prepare the maximal entangled quantum state. Okay, this is the condition to achieve the maximal value. And I don't know if I can erase my notes here. I think yes. But this is the scenario. We have a source. The source prepares maximal entangled state. In this case, for this inequality, we prepare two entangled qubits, right? And Alice has the four measurements. Three of them are projective. The fourth is a POVM. Bob performs three projective inequality measurements. And here is a little picture about how we can implement the POVM considering the polarization degree of freedom of the photons. And do you know how we can implement a POVM theoretically? I like to ask questions. Do you?
Do you theoretically know how to implement theoretically?
She is raising her hand.
I think one way is implementing a PVM on a higher dimensional system and tracing it.
Okay, yes. Yes, this is the Neumann theorem, right? The Neumann theory states that if you want to implement a POVM, you need to couple an ancilla to the original system and then perform a projective measurement over the total states, and then you need to trace out the ancilla. So this is the way which we can implement a POVM. There is another way to do that. It's called the direct sum of the dimension of the Hilbert space. So I will explain this specifically this method later with the multiple fibers. But in this case, we are using polarization qubits, I don't know if you see here. This is the input of this blue region. The blue region corresponds to the implementation of the POVM, and our ancilla here is the path. Right? So keep attention to this. We have here a polarization qubit. And here we have the polarized stability splitter, which I introduced to you the last class. So the PDS reflects the vertical polarization and transmits the result of polarization, right? So the vertical component is reflect, and sorry again. And we have here two wave plates, two half-wave plates, just to rotate the polarization ball in each path. Okay? So if we have the horizontal polarization at the input of the PDS, the horizontal polarization goes through this path. This half-wave plate rotates the polarization, so you have now a superposition between the horizontal and vertical polarization, and then we come back to the PDS, and then the vertical polarization reflects to this path, and the horizontal component goes to this path. Okay? The same thing occurs for the vertical polarization. So at the end, we can have these three outcomes. Okay? And when we're talking about the trace out ancilla, it's just detecting these three paths. Okay? And this is a simple way. A simple way to implement a POVM with three outcomes on qubits encoded in the polarization degree of freedom. Okay? So we implement this experiment in 2016 with the collaboration with Adam Cabello, Matthias Kleiman, and Thomas Bertzi. And that experiment was so difficult because in order to achieve this region, this green region here, we need to have an excellent quality of polarization entanglement and very, very precise measurements. That means we need to put the wave plates, I think we were using just half-wave plates, but we need to put in the certain angle, and well, we did that. So with our statistic, we enter in this green region here. So the conclusion of this experiment is our statistics recorded from this experiment is incompatible with statistics obtaining just using a dichotomic measure. So our device is a genuine implementation of a PVA. Okay? But what about in higher dimensions?
There's a question.
Sorry.
Is it possible to implement a POVM without using a PVM throughout the process? You always have to evolve a PVM in your measurement, or?
I guess yes. I guess yes. In the both experiment that I will show you, this one and the other one, we always make project measure in a larger hyperspace. That is the idea. Or in this case, trace out and see. But we always perform PVM. Okay, PVM, what is the meaning of PVM is positive value measurement, right? Projected value. So but for me, a PVM, the projective measurements also are PVMs, so it's the same. Yes?
But cannot I think also that in a way we can never perform perfect projective measurements. So even if we try to perform PVMs, at the end we're doing a POVM. Does that make sense?
Sorry, I didn't get you.
It's like, even if we try to perform PVMs, if
Yeah.
our measurements are not perfect, so we have loss at some point, it's not a PVM. So it
In some way,
yes. Okay.
yes. But depending on the experiment, I don't know. For me, I'm interested in, I don't know, some fundamental aspect of quantum mechanics or a proof of principle experiment. So we assume for the first sample assumption. So we are concentrating just for the detected particles. So the description of this experiment is using PVMs, okay? But there are other experiments which we require to implement the PVMs. For instance, quantum state discrimination, randomness expansion, certification of randomness over qubits. I don't have time to show that experiment, but we can talk later about it.
Okay, thanks.
You have another question?
Hello. We know that when we are dealing with entangled states, there are entangled states. There are some entangled states that don't violate Bell inequalities. In this case, do you have POVMs where this is not valid, or you can build a Bell inequality to certify every POVM?
Yeah, well, it's a very good question. The device-independent scenario requires a violation of a Bell inequality, but you don't assume anything about the inner function, the inner functionality of the source and the measurements. So you just have access to the outcomes. So the point here is, if you have a table with the probabilities and then you compute inequality, and for instance you obtain, in this case, 1.1, you cannot say anything. But if you repeat experiments in other conditions and you obtain 1.299, this is the perfect value, okay, so your conclusion is this device, I don't know how it works, but this device is a POV. Okay?
Steven. Hi, sorry. I don't know if I misunderstood the experiment, but are you co-propagating two polarizations in the same interferometer?
Yeah.
At the same time?
Yeah.
How are you measuring it? It's tomography?
No, I mean, well, okay, but this experiment was not my intention to explain, but here we have, where is the scenario? Where is the scenario? Come on, where is the scenario? No. So the idea is, in our experiment, the source emits two photons in an entangled state, in the maximal entangled state. Okay?
Alright.
So the maximal entangled state for this experiment was in polarization. Okay, let me change here. Probably you know the notation, right?
Alright.
This guy here. So one photon goes through Alice, but you don't know where is the polarization state of this photon, because they are entangled with the photon of Bob, right? So in the interferometer, which is a Sagnac interferometer. The Sagnac interferometer is a very, very useful interferometer because the two paths inside interferometers are the same.
Yes.
So you have a locked phase in the interferometer instead of the Mach 7, for instance. And so to do the analysis of how this interferometer works, you need to test if what happened with the the horizontal polarization, with the vertical polarization, and then.
All right. Do you think it would be suitable to try to do with intensive beams using Mach-Zehnder and transverse mode instead of polarization?
Yeah, but the Mach-Zehnder, as I said, it has a very, very big problem, which is the stability in the phase.
Could use PZT.
Yeah.
And try to improve the phase dynamic.
Yes. Yes,
it would be
you're right.
really hard, but
yeah, it's hard. The Sagnac is much more easy.
All right. Thank you.
I love Sagnac. But I don't have much time to talk about that experiment, but the source also is a Sagnac interferometer. But now I want to talk about what happened with POVMs in higher dimensions. Okay? And this is because we have the multicore fibers. And we have the new technologies of our devices that are compatible with the multiple fibers. I mean, the multiplexer and the multi-port beam splitter. Okay? And in Concepción we have a multi-core beam splitter with 7 cores. Okay? I will show you later some pictures. So the idea is, okay, we have the multi-port beam splitter, which is this gray box. And what happens if we excite some modes at the input, not the total modes available for the multi-port beam splitter, just a few modes. The cardinality of this mode is D, and we access to the all modes at the output, labeled by capital T. Okay? And this is an implementation of a POVM. This is a question for you. I think it's more simple to think for the four-path multi-core beam splitter. If you illuminate 2 cores, and then you have the multi-core beam splitter with 4 cores, how many cores are illuminated at the end?
Depends.
Four?
Depends on? It's my class, I have to tell you. Okay. But in principle, don't forget the polarization. For now. In principle, we can have the 4 cores illuminated. Because as Steve showed you, the cores are so close in the tapering process, so we can have the coupling process between the 4 cores. So, in principle, we begin with a qubit, and at the end, we have a Q-quart. And if we detect, and if we place detectors after this multi-core beam splitter, well, I can say that I implemented a POVM with 4 outcomes. And also, Steve showed to you that we can put a phase shifter in each arm in order to implement another kind of unitary process which leads to other implementations of other POVMs. Okay? POVMs acting on qubits, it's okay, because I recently presented to you an experiment with that. Our interest is go to the high dimensional quantum information. High dimensional quantum information has a lot of advantages. For instance, they present advantage of, in some protocols, for example, for cryptography, to certify more than one random bit instead of qubits. And also, if we want to get entanglement between high dimensional quantum states, there are a lot of Bell inequalities which requires lower detection efficiency, so you can avoid some loopholes. Okay, so it's relevant and it's important and it's interesting for us, we have this technology to create, manipulate, and detect not only single qubits, but also entangled states. Okay? But now, I keep going with the POV. In this case, okay, I think that I showed to you this slide the last class. Yeah, Daniel asked to me about this number. And if we think that this multi-port splitter is the 7 core beam splitter, kind of very difficult to talk about everything about fiber, optical fiber, but don't worry. And for the case of 7 outputs, and if we want to illuminate 4 cores, that means we are interested to implement a 7 output POVM onto a qubit, right? We can have 35, I think. I don't remember exactly the number because I'm very bad at remembering numbers. But yes, here you are. 35 possible POVMs. Because this is the matrix which represents the multi-port beam splitter for 7 cores. This matrix can be obtained by a process tomography that we perform in Concepción. And considering this matrix, we can find each POVM depending on the input cores which are illuminated. So, for example, this is the POVM where we connect the core number 4, 5, 6, and 7 in this configuration. Can you see that? I think yes. So if you illuminate another core, if you connect, I don't know, the number 1, 3, 7, and 4, you have another kind of POVM. Right? And the question now is, okay, can we certify this implementation of the POVM? With a little constraint, without entanglement. Because entanglement, I love entanglement, it's very beautiful, but it's a pain. Oh, you can start thinking about entanglement because I'm going to ask to you what is your opinion, what is the definition, what do you think about entanglement? Well, we resort to the prepare and measure scenario, and we can think this scenario as a game in which Alice and Bob want to play a game. In this No, sorry, so before that. The prepared measure scenario is much more simple than the device independent scenario. Sometimes it's called the semi-device independent scenario because you have some assumptions that in the device independent scenario you don't. Okay? So, for example, in the prepared measure scenario, you have to assume the dimension of the system. Okay? So, in this case, Alice has a source, Alice has a box which prepares states. And these states are sent to Bob, and Bob has another device which implements measurements. And then you can construct this in the same way I mentioned before, probabilities. The probability to obtain the outcome B when Alice sends the X state while Bob performs the Y measurement. Okay? So, what we can learn about, or from this statistic, from this list of probabilities? Because Alice can prepare n plus 1 states, Bob can perform n plus 1 measurement, and Bob also, each measurement can have p plus 1 outcomes. So, what we can learn from that? And, well, this is a recent work from Matthias Kleiman and his group in Germany, which they propose the minimal scheme to certify a POVM on qubits using just, I don't remember, but I can read the abstract very quickly. Not very quickly, sorry. I think they need just 2 input, 3-state preparation and 2 measurements. One is a projective measurement and the other one is a 3-outcome POVM. But it's almost impossible to implement in experiments because the same reason that I told you before. The gap between the both strategies using dichotomic measurements and projective ones, non-projective ones. Okay? So, we can go to this game. And this game requires that one measurement in both is a POVM. Okay? So, this is we can think this protocol or this scenario as a quantum game, right? Sorry. So, let's play. We have this scenario. We have Alice with 7 preparations of Q-quants, right? So, the box of Alice can prepare 7 different quantum states of dimension 4. Alice sent 1 state to Bob, and the idea of this game is that Bob tries to guess which is the classical input that Alice used to send her state. It's clear for you? So for instance, Alice pressed the second button represents the second state, so Bob wants to guess what number used Alice to send me the state. So the only way that we have in nature to achieve some information from nature is making measurements. So Bob presses some buttons in his device, and depending on the results of his device, he could earn some points. So the idea is the following: if Alice sent the X value encoded in the quantum states. Bob, okay, pressed the Y button, and he obtained the outcome 0, B equals 0. He earns 1 point. So Bob press the button, the red light turns on, okay, 1 point. If Bob obtained the outcome B equal to 1, in this case the green light, he can earn 2 points. I didn't write the rules of the game here, sorry. But here's the key of this game. Bob also can perform an 8th measure, which is a POVM. A POVM with 7 outcomes. Very convenient. We have Q quarks in multiple fibers, and we have a 7-core beam splitter. Okay, let's play it. If Bob chooses to implement the POVM, if the result of Bob, which is labeled by B prime, is equal to the value of X, he earns 3 points. Okay? So the game can be written in this way. Here's the term related to the POVM, and here's the term related to the projective measurements. And here we have 1 point if X is different from Y, and we have 2 points if X is equal to Y. Okay? So if we, at the same spirit that we explored for in the case of the Bell inequality, here we can implement all the strategies involve just projective measurements. Okay? And the maximum points that we can earn in this game using projective strategies is the value here. Okay? But if we resort to a POVM, the maximal value, which corresponds to the maximal quantum value, is given by this one, which is greater than the other one. Okay? However, to obtain this value here, we need to implement a certain POVM that we cannot implement in our labs due to the lack of technology. But, as I told you, we can implement 35 different POVMs. So we made a search among the 35 POVMs, and we found that one of these POVM, the POVM 4, 5, 6, and 7, which gives to us this value, which is greater than the projective value. Okay? So if we implement an experiment where we implement this POVM and we obtain this value, so we are certifying that our POVM or our implementation of the POVM is genuine. Okay, this is the experiment. You can see the details of the figure.
Yeah.
You can. I don't know if I can take a zoom. I guess yes. Yes. Well, this is the experiment. We have a laser in the telecom wavelength. We use an attenuator in order to lower the power beam, and we have a Mach sender. This Mach sender is just to go for the single photon level. Okay? Here we have the multiplexer, the 4-core multi-core fiber, and then the debugs. Here, I don't know if I can now, but at this point here, we have now uniform superposition of these two parts. Okay, and then we again implemented the multiplexer, and we have some phase modulator, intensity modulator, just to prepare the states that are required for our protocol, right? And this is the ALICE size. So all the gray box is the gray box that I showed you before for ALICE. And then we connect to Bob. Bob actually in the lab has two boxes. One box corresponds to the projective measurement and the other corresponds to the DOVM. Okay? And I don't know if you remember how it is the implementation for measuring polarization units.
Marker, Alf, and PBS.
Sorry again, I didn't hear you.
Marker, Alf, with plate, and PBS.
Yes, and what represent these two wave plates?
Rotations and bases.
A unitary transformation, right?
Yeah.
You said the same thing. Okay. So here, if we want to implement a measurement, but now over the paths available in the multi-core fiber, we need to implement these unitaries too. And to perform these unitaries, we need phase modulation, the wave plate 1, intensity modulation, wave plate 2, the multi-core beam splitter, PBS, something like that. No, it's not clear the parallelism between them, but it's just to you to obtain an idea how the measurement process works, and then we connect each path to the detectors. Always we detect the logical basis, but each path here, due to the unitary process, represents the outcome, the projection over some states. And these states represent the measurement basis that I implemented using this unitary, right? For the POVM, here this sketch is very well done because we are illuminating number 4, number 5, number 6, and number 7 core. We connected these cores into the MOOCs of 7 cores. We have here the multi-core beam splitter with 7 cores and the MOOCs, and then we connect each single fiber after the multiplexer in order to detect. Okay, so here I have some examples. This is an example of a projective measurement. Okay, the experiment is the orange bar, the theory is the blue bar. The projective measurements are pretty good. This corresponds to when Alice sent the 6th state and both perform the 4th projective measure. Okay? Here's another example, but now for the POVM. When Alice sent the 7th state and Bob implements the POVM. You have a question?
Yeah, I have to say I'm from theory, and for me it's quite difficult to read with plots. So maybe my question is not really related, but yeah, I'm wondering. So from what I understood is that you do a projective measurement on the 7 cores, and trace out some to have a POVM there. But the projective, from my imagination, the projective measurement has to be on all qubits together and is not separable. But this picture looks like you're measuring each core.
Each core.
Qubit.
Okay, yeah, but first of all, this scheme to implement the POVM is different from the polarization POVM, right? In the polarization POVM, we need to add an ancilla. Here, we expand the hypertext space using other modes in the multi-core beam speed. Okay? And what was your second question? Sorry.
So do you do measurements at the end, which are, do you do separable measurements at the end?
Ah, okay, yes, because it's not possible to put in the same experiment, the same arrangement, the projective and the POVM. So we need to select randomly if both performs the projective or the POVM. It's
When you
something like that,
perform,
or
I have a question as well. So when you perform the projective measurements, you just discard the other 3 cores. So you're looking at clicks.
no, okay, no. To implement the projective measurement, we use the 4-core beam splitter. The 4-core beam splitter. That is the reason that we have 4 results here. But for the POVM, we use the 7-core multi-core beam splitter. 7-core beam splitter.
Another experiment.
Okay. That was your question. Something like that. We can talk later. Another question? Or another question? Cool. So, I don't know how much time we have. This is our result. This is the 25 minutes. Okay. This is the projective bound. So if you stay here, you lose the game, right? This is the region between our experimental bound. Remember that we cannot implement all the POVMs until now. We cannot implement all the POVMs because we need to perform, I don't know, some phase transformation, intensity modulation that we didn't this kind of transformation in this experiment, and this is our result. Okay, so we're pretty far for the projective bound, and this is the maximal value of the game. Okay, so we can say in this experiment that our system again is a genuine implementation of a POVM.
Esteban, can you describe?
Yeah.
Can you describe a little bit how the experimental bound is calculated? What
The experimental bound?
Yes. What you?
Yeah. No, it was a numerical search. Okay, so we have the list of the 35 POVMs, and then for each POVM, we put on the optimization problem in order to obtain the bound of the maximal value of the weakness in this case, and the higher value for our POVM was that.
So it means that the best strategy is another POVM.
Exactly. Yeah.
It's not
Exactly. The best strategy to obtain this value here is another POVM that we cannot implement in our lab.
Still, as we say in Portuguese or in Brazil, I'll take a ride with somebody else's question, previous question regarding the fact that any experiment that we do indeed does not really make a projective measurement, but make something close to it, can make something close to it, but not really projective. And then my question would be, if you are actually distinguished from projective bounds. Well, projective bound is a mathematical calculation,
Yeah.
fair enough. But like, in some sense, it would be more fair to say that your left side is the result of a 4-output POVM that is very close to what would be projective measurement, whereas the other is a result of a 7-output POVM, something like that.
I don't know. I'm not pretty sure. You mean in the expression of the W here? Oh, okay. I put here just one example because we have to implement 49 predictive measurements. So I don't have space now, but I don't understand really your question. What is your point here? It's more useful to separate the both strategies in this way. Are you asking?
I'm asking more in the well, let me put it in a bit different way. Go back to the bound graphic.
Oh, here.
Yeah, so I'm asking more like, I see a projective bound that is 62.5152.
Yeah.
So this is mathematical bound, for sure. So, but then, if I want to compare anything to any experiment, if I want to be reasonable in terms of experimental results, shouldn't I make a blurred bound? I'm not talking about your result. Obviously, because of the size of your bar, error bar,
okay.
you are well within the experimental projected bound. So, but I mean, so this strict bound will not correspond to any experiment whatsoever. So my question is, shouldn't we use kind of a blurred bound or something like that? Considering your experimental errors, that's what I mean.
Yeah, well, let's say you are talking about in terms of the standard deviation of our results to compare with other experiments. Yeah, it's a good question. It's a good question, because in this case, for this experiment, which is very, very difficult, here we put the standard deviation. So to combine all people, okay, we are very, 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 very far for the project bound. In this experiment, the other experiment, as far as I know, our experiment was the first using this kind of a strategy, and I think we define, how can I say, the benchmark of this result. So I don't see any experiments in this way, and at that time where we are discussing about this, because we have that discussion, is these error bars are enough to present our results or not, and we said yes because of that. This is the first experiment using this strategy in the prepare and measure scenario. So, Thank you very much for the questions. And here I have a take-home messages. The first one, POVMs are relevant in quantum information. Not only from a fundamental point of view, because all of the works related to the certified POVMs are related to the concept of the dichotomical future of the nature. If there is it possible to simplify our description of reality in terms just on dichotomic measurements? And the answer seems to be no. Okay? Also, for protocols in quantum information, as I said before again, we use the POVM from quantum state discrimination, we use the POVM for certify different amount of randomness, we use POVM for quantum state estimation. We can find Bell inequalities which are more robust using POVMs. So there are a lot of things that we can do with POVMs. Okay? Several tasks require entanglement, especially in the device independent scenario, which again is related to Bell inequalities. Semi-device independent scenario, in this case, don't require entanglement, but the semi-device independent scenario, in this case, you can make more assumptions of your system, so you can use this advantage for implement other protocols. For instance, remote state separation using an steering inequality, for instance. I don't know. And the most important thing for us, multi-core fiber-based technologies allows us to implement this kind of things. Okay? And now, I'm going to talk about entanglement, if I have time. Probably I have 15 minutes. 15. Yeah. So, well, this is the slide. This is the very simple definition of entanglement, very basic. But I would like to hear you about what is your opinion about entanglement. Don't be shy. Anyone on this room understand pretty well this concept, I think. But it is the most beautiful concept in quantum mechanics, in my opinion.
Information.
Don't be shy, be brave.
Just to be sure if I understand, what do you mean by my opinion on entanglement?
In my opinion, because there are other models, other scientists that doesn't believe in entanglement.
Just like there are people that don't believe in speed and stuff like that.
Yeah.
Although I really like entanglement. I work with entanglement. I try to deliver entanglement, and I also really feel that it's one of the most amazing concepts that we have. And like the whole idea when you see the idea of Bell, like showing that you have a bigger space of possibilities, then you have only this combination of states. But then when you see it in the lab for the first time, you do stuff together and you see a line that's going below. It's just amazing. Yeah, it's a great concept there.
Yeah, thank you. Anyone else? Do you believe in entanglement? This is the Church of Entanglement.
So, is there anyone who doesn't believe?
Yeah, I know.
We're not. This is not really a church or a religion. It's not a matter of believing. Is there one that contends say that the entanglement is not?
Yeah, I am one to pray for other church And
The church of contextuality.
that entanglement is a very beautiful thing, but we should not believe that it's the mystery of quantum theory, because there are prime numbers. Sorry. We have interesting quantum features in Hilbert spaces of prime dimension.
No. That's a completely different question. It's not if entanglement exists or doesn't exist.
No, the question was if it exists or if it's the most beautiful one.
No.
The existence I don't deny, actually. But if I understood, the point was it's the thing, and I believe it's somehow overvaluated, even if it's very important and very interesting.
Thank you, Marcel.
I just kind of have a question about the slide because it says that it represents correlations between physical systems that any local theory cannot explain, but can't you, I was under the impression, can't you preserve locality if you give up like objective realism? Or no?
Sorry, what?
Can't your theory like still be local if it's not realistic? Like objectively realistic?
Actually, I don't know. But I know that I don't remember in which year I read a paper which states that any general theory beyond quantum theory requires entanglement.
But is it non-local because of that?
Well, there are some difference between non-locality and entanglement. Strictly speaking, it's not the same. They are not the same.
Okay. Yeah, because I was just wondering with how it was phrased, it looked like the entanglement only exists if it's not local. But I was thinking it can't be.
But the elements are not local correlation.
What's the difference between the correlation not being local and the theory not being local? I don't know if I get that subtlety.
In terms of Bell non-locality, in which you can construct a model with a local hidden variable, which I forgot the word, which can reproduce the same statistics from the quantum mechanics.
Yeah, okay, I understand now. Thank you.
Right, you're right. I'm going to next slide. But by the way, entanglement, as Marcelo said, I agree with you. Probably this is not the best and the main important concept in quantum mechanics. There's a lot of things that are very, very interesting. But entanglement is a powerful concept. It's a powerful concept because it allows us to discard this kind of theories, local hidden variable theories, non-local hidden variable theories, and also entanglement can be used as a resource for some quantum information projects. For instance, teleportation, dense coding, all related to the device-independent scenario, obviously, as I said. So, all the story begins this year. Do you know this paper? Yes. Are you reading it? Are you understanding? It's a very, very tricky question. No, it's a very nice paper. I cannot explain the paper, but it's a very nice paper. Okay. It's the famous EPR paradox. What is the main result from this paper? All the quantum information community must know. Must know what is the main conclusion of this paper.
Einstein was wrong.
the description. So you okay. So if you assume that if you can predict with certainty the value of a property without disturbing the system, then there is an element of reality that corresponds to that property, and you assume that action at a distance is impossible, then you have to admit that the quantum state does not provide a complete description of physical reality.
Okay, thank you very much. We can do a philosophy meeting after that. Philosophical meeting after that. About physics here, with some beautiful questions, but I don't know if you agree with me. But, well, yes, the main result here is a question, or the quantum mechanical description of the nature is complete or not. And Einstein, Podolsky, Rosen, they think it about. And then this was in 1935. In 1964, almost 30 years later, John Bell published this work here on the ancient Podolsky-Rosen paradox. And the most important, to me, okay, this is for me, the most important contribution of Bell from his paper is that he gives us the possibility to experimentally test if the quantum theory is complete or not. And that is awesome. It's a pretty simple work. It's a pretty simple mathematical expression. It's a pretty simple idea of experiment. But it's a very, very hard experiment. Allen aspect going to perform his experiment in 1980, and the last year with Seidel and Krauser, they received the Nobel Prize for it.
And when was the first time you met Alan Spade?
Oh?
And when was the first time you met Alan Spade?
Tricky question from you, Marcelo. Yeah. Here in Paraty, 2009, Alan Speck was one of the lecturers of that school. Okay, do you know this expression? Very good. I love it. Well, here's some pictures of the Nobel Prize, and well, Alan Speck was in Chile, in Concepción in 2019. Here's some of our students. They are not here. But the question is, or the point is now, okay, entanglement is very interesting, it's required for something, so how we can get entanglement in the lab? Steve, where's Steve right now? Okay, so, how we can obtain entanglement in the lab? We resort to the nonlinear process called spontaneous parametric time conversion. Spontaneous parametric time conversion is the optical process where we have a pump beam, a laser beam. This laser interacts with a nonlinear crystal, and with some probability, one photon from the pump is absorbed by the medium, and then the crystal emits two new photons, which has some interesting properties. Okay? I left this slide in blank because I wanted to write some things here. but it is pretty simple. Do you know that when an electric field interacts with a medium, the electric field induces a polarization in the medium, right? Do you remember that? So, the polarization of the medium is proportional to the electric field with this relationship where, how do you say, Ki, in Chile is chi. I'm not Greek, I don't know. Okay, but the effect, it's a non-linear effect, so you need to consider the second order in this expansion here. So you have to put here the second order tensor of the susceptibility, and then you have here two fields. Okay, so then you need to construct the Hamiltonian, which is related to the energy in the medium, and this term here corresponding to the non-linear effect on the polarization. You can split the Hamiltonian into the first order Hamiltonian, the linear, and Hamiltonian of interaction, which corresponds to the non-linear part. Okay? And we have to, if we want to know the evolution of the vacuums in the medium, we need to apply the unitary evolution considering this Hamiltonian, right? So I have my note because I don't remember exactly how it is. So we have what is the final state. We need to apply the unitary transformation, and the unitary transformation is it's exponential, but we expand in power series. So we keep just the second term, and the second term is proportional to I don't know this factor here, and we have here an integral in time because this process occurs in the time interaction time. So we have here the interaction Hamiltonian. Okay, so if you apply this evolution, unitary evolution, you can obtain, after some calculus, some algebra, a lot of things, approximations, blah blah blah. I don't know why I cannot write this. Thanks for your patience. We have something like this. This is the state of the down-converted photons. Okay? The photon from the pump is destroyed because we can. Well, it's pretty simple, the idea. In the Hamiltonian, in the Hamiltonian, you have the electric field, the displacement, you have the magnetic field, blah blah blah, and you have to quantize, the electric field in this case, and to do that, the canonical way to do that is to expand the electric field in terms of plane waves. And you have the amplitude of these plane waves, then you have to convert to operators, and you have annihilation operator for the band B, and you have creators operators for the beams related to the signal and either fields, which correspond to the down-converted photons. So, here again, we have this. The first step is the most typical. 0, the backbone. Because the process is very, very inefficient. But the second term is related to the polarization modes. And if we place some interference filter, that means we are looking just for a certain region in the wavelength. We only care about the spatial correlation. In this case, we have these two functions here, which cannot separate between the transverse momentum of the single photons. And this is the signature of the non-separability of this state. Either signal is the typical name for the down-converted photons. For one, a signal and signal. Okay? This function here represents the pump beam distribution. This function here represents the phase matching conditions in the nonlinear process. It's how how in the nonlinear media the wave vectors match in some way. And the most important thing here is if we write this state here in terms of the position of the photons, this function here becomes very narrow. So in coincidence, if we detect the position of one photon, if we detect the position of one photon and the other, both photons are in the same place. Okay? So we will use this part to, okay, I'm going to directly to the intended source using multiple fibers. We use this fact that in the center of the crystal, in the born region of the down-converted photons, the down-converted photons are in the same place. There are two works from South Korea where they implement a source to create Q quarks, but these sources are very, very inefficient because they put, for instance, here the two multiple fibers in a beam. So they lose all the light, just couple a little regions of the down-converted beams. Then they try to improve this using the spatial light modulators, but you know, all people that are working with SLM, you know that there are a lot of problems using the spatial light modulators. So our idea was to build a source of qubits, but compatible with all the technologies with the multi-core optical fibers. So this is our source. We have a laser. This laser is operated at 773 nanometers. We connect the fiber into the multiplexer. We have here the multicolor splitter, and then we use an image system where we create the image of the output of this connector at the center of the nonlinear crystal. Okay? So, what is the idea here? We don't know where the photon from the PAM is from. I don't know if the photon is in the 0 core in this codification, or is in the 1 core, or is in the 2 or 3. So the state of the PAM photon is a superposition of the 4 available paths. So the crystal, we considering this process as a coherent process, we don't know in which region of the crystal the crystal is emitting down-converted photons. So we can get 2 pairs located in the 0, or 2 pairs located in the 1, or 2, or 3. So at the end we have this state. Okay? And obviously we need to characterize the source. In principle, we need to, we have several ways to certify entanglement. One is make the tomography of the state. Another way is to implement a Bain inequality. And another way, this is, I think is more easy, is to measure 2 bases. Because entanglement is independent, is invariant under change of basis, right? So here we are measuring the logical basis, so we don't connect anything here, just the multiplexer, and we measure the coincidence in each single fiber after the multiplexer. But to implement another basis, we need to use the multi-core splitter. As we implement for the case of polarization, we need to implement the wet plates and the PVAs and the detectors, right? It's in the same spirit. So we have here the implementation of complementary bases. Here is the multi-core beam splitter. Very difficult to say. And then after that, after the multiplexer, we measure the coincidence between the trigger and the detectors. Also, here we have a big problem. We don't have any control over the phases. It was a technical problem. Okay? But this is a picture of the source. But we need to study the stability of our source. And performing a Fourier analysis of our signal, we found that the fluctuations appear after 5 minutes. After 5 minutes, the system begins to change. It begins to move to another phase. So in 5 minutes, we say that some phases are implemented in our experiment. So we use this fact to extract the results in this time, and then we say, okay, this is some basis. We wait to another time, we wait 5 minutes, and extract the data. There are very peculiar feature of our system. Every change of phases move one basis to another, which are mutually unbiased. In this case, for example, the logical base has 4 maximum values, the other are 0, but for the other bases, we have the same behavior. As if independently in which phase we are. So we using this feature, we can estimate the fidelity of our state to the target state with the maximum target state is 0, 0, plus 1, 1, plus 2, 2, plus 3, 3, blah, 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 and we obtain this value here. Okay, you can say, oh, this value is slow, doesn't matter, because there are criteria which say that if my fidelity is greater than 3/4, so my entangled state is incompatible with any entangled state with a Schmidt number below than 3. And the Schmidt number is related to the dimensionality of our entangled state. So we have, in fact, we have a two four-dimensional entangled state using multiple fibers. So, final remarks, final words. We can prepare, operate, measure photonic quantum states in multiple fibers. We can implement generalized quantum measurements. We can build entangled source. And we have a to-do list in blue. We need to perform an active control of phases in order to get the control of which phases I want to perform. We need to prove the architecture of our source. I didn't have time enough to explain this, but it's our task. We need to optimize the detection scheme. We are working the down-converted photons are in the telecom wavelength, and the detectors in telecom wavelength are very, very inefficient. So we lost a lot of photons. Okay, Steve told you that we have in the university a network in the campus using multiple fibers. So I would like to distribute the entanglement that we prepare in the lab to the other labs. And why not prepare multipartite entanglement? And finally, I would like to show you a quote that I love it. Thank you very much for your attention, for staying here. I hope that you have enjoyed Paraty, enjoyed the whole trip. See you in another occasion, whatever. This is the quote.
Thank you very much, Esteban. Thank you for opening space for the audience to talk, for asking questions.
Yes.
Your
It's a
explanation,
class.
yes, your explanation about the SLC process was really good and short. I enjoyed it very much.
Thank you very much.
And the stuff you are doing with the fibers in Concepción is really amazing. Congratulations, thank you very much. Maybe a quick question, just for...
Now we have a test.
Oh, yeah. We have a quick question for us to finish your talk.
So maybe it's a long question, so maybe you can talk in English or something. I have a very provocative question.
Provocative question, okay.
Yes. When you violate the Bell inequality, it implies that some assumptions that you made are wrong. There are always three, but there are some extra assumptions. So I don't know, they're very weird, like logic doesn't work or statistical independence. So what's your opinion about that? Is there a place for still exploring that, or do you think it's settled?
I will invite to you a beer, and then we can talk about no. There are some reasonable assumptions that we can take into account. For example, the locality condition. We need to separate the labs in order to avoid any causal communication between Alice and Bob. But there are other models which is impossible to discard, because I think these models, they are not more physical. For example, superdeterminism. I don't know how we can implement, or how I can propose an experiment in which we can discard superdeterminism.
Okay.
I think this is very interesting, but it's more a philosophical question than a scientific question.
Yes, so that's why I said it was a provocative question. So do you still think there's a place for that?
Sorry?
So do you still think there's a place for exploring, at least in theory, these things?
Yeah.
Okay, thank you.
The invitation is open.
What is the size of the system of entanglement in the university? Of the distance from one lab to another?
What are the distance between in the link, in the optical link?
Yeah, for entanglement in the university.
I think between the two labs that are in the second floor, there are 20 meters of link. To the sixth floor, I don't remember, probably you know. Huh?
100 meters?
100 meters, and to the engineering faculty, I think it's 800 meters. So in total, it's almost 1 kilometer.
It's really nice. I've been there. I've seen it. It's really nice.
Okay, thank you.
Thank you. Sorry to bother everybody. To summarize what I understood about your technology, this multicolor fiber and stuff, it seems to me that they are indeed amazing to transport, to propagate different spatial modes. But since you cannot address individual phases for each spatial mode, I don't know how good they are to operate, to make operation, to perform gates or something like that. Like indeed the experiment that Professor Warburg showed us last lecture, that was really amazing because it's something that really probably you cannot do with several different fibers. While in contrast, this experiment that you showed us today, it seemed to me that it's kind of more complicated than doing that with a chip or something like this. Do you agree with me, or am I missing something?
No, you're right, I think. Well, the main idea or the main motivation to use the multicolor fiber is that we can build some devices that we can access in real time to set up this instead of the photonic circuit. In the photonic circuit, you build a circuit, and these circuits perform the same thing every. Okay. For multicolor fibers, we developed the technology of the multicolor beam splitter. We have the multiplexer, and at the end, it's just a plug and play technology. So, if you want to perform a unit,
Most of the chips are reconfigurable nowadays, right?
yeah, the novel series, but okay, yeah. But our system is plug and play. If we want to perform a phase operation in our system, we just disconnect the fiber, we put the phase modulator, and so on, and that's all. If we want to implement an intensity modulation, it's the same thing. The technical issues that we have now is when we work with entanglement, with our intended source, because we need a signal over the entire experiment, which is our reference, right? Because all of our system is a very big interferometer. So any fluctuation, any mechanical fluctuation, thermal fluctuation, blah, 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 change the statistics at the output in the detector. So we need a reference in the entire experiment just for lock the phase. In our experiment, considering the entangled source, it's very difficult to implement the reference because we have two lights. We have the band beam which is in one region in the spectrum, and we have the down-converted photons which are in the other side of the region of the spectrum. So we need to stabilize both. And this is the reason that is for now. But we are working on it. I think we will have results. I hope. I'm praying for that.
I will. Okay, let us thank Esteban again. I'm really amazed to see all of you here. While Esteban was talking, I counted how many of you there were, because we're going to play a quantum game now. And the prizes for this quantum game, they're like rollouts t-shirts, rollouts snacks. There are board games provided by Carlos from Paraty show. There's Carlos coming here. And there are a bottle of cachaças. So I'm going to pass a box. I'm going to, each one of you, I'm going to take 6 numbers from this box, okay?